Hey physics students, I'm going to give you some notes here about projectile motion. At this point you have done a lab, so you should have some idea about what I'm going to tell you here. First of all, what does projectile motion mean here? This is motion of an object that is only under the influence of gravity, nothing else. So, for example, is this calculator in free fall? Or sorry, is it experiencing projectile motion? No, because it is certainly it is under the influence of gravity, but it's also being pushed up on by this this little table here. What about now? Is it in projectile motion now? No, because now it's still under the influence of gravity, but now it's also under the influence of my hand and the various different changing forces as I turn it over in my hand. So projectile motion is something that has been launched through the air and that is only under the influence of gravity. So there are situations where, like, once we get into, if things are moving fast enough, then you really can't ignore air resistance, and that changes and makes the problem more difficult. So right now what we're talking about is situations where we can and will ignore the effects of air resistance and any other kind of like aerodynamic effects like lift or drag or whatever. So effects of the air. So this is only under the influence of gravity. Can you get away with that, with ignoring the effects of the air? Yeah, at lower speeds you can. It works just fine. And with many things in physics, you have to start with like a kind of simpler model that doesn't take into account everything before you can develop more complicated models. If you're wondering to yourself, well, are we going to be working up those more complicated models with air resistance and everything? Yeah, we're going to deal with air resistance much later in the year. There's some calculus that we don't have yet that you need to be able to do that. But we'll only do air resistance and like drag forces in one dimension. And that will be much later. Okay? So, what's up with projectile motion? Here's what's up. You probably know this already. If you consider the horizontal and the vertical components of the motion separately, the horizontal motion is constant velocity. And that should make sense. Gravity, as something goes through the air, its horizontal motion is not affected by gravity. Gravity does not care about the horizontal direction. Gravity is an up-down thing. Or if you zoom out enough, it's a toward the center of the Earth thing. But, locally it seems like, because the Earth is locally flat. Oh, that sounds like local linear approximation, huh? Since the Earth is like locally flat, those lines that go toward the center of the Earth really look like they're just parallel going straight down to us, even though they're slightly in like this toward the center. It doesn't matter to us on a local level. Horizontal motion is constant velocity, and that means what mathematical models or equations do we have? That means that your displacement delta x is equal to your constant velocity, which I'm going to call Vx, so as not to confuse it with other Vi's and Vf's, times time. The vertical motion of a projectile, as you already know from doing this in Chapter 2 with one dimension with free fall, vertical motion is constant acceleration. And what does that mean for mathematical models? That means in the vertical direction, you use the kinematics equations. And with knowing that if you're talking about projectile motion on our planet, then your acceleration is 9.8 meters per second squared in the down direction. And if you have decided to make down negative, that would be negative, right? But I'm just going to say down here because and I can leave that decision to be made later. All right, great. So what does it look like to solve a projectile motion problem? How does the work look? What does it feel like? I will give you, I think, one example, and then I will post a video also of the book problems. So if you get stuck along the way, you can bounce back and forth with that video. So here's an example. Excuse me. So let's see, here's the ground. Let's say we're going to launch something off the top of this building. This is a building. There's a door. I don't know what's inside this building. I've never gone in through that door, but there's some windows. And on the top of it, there's a person who is throwing things. And they're going to throw something with an initial velocity of, let's say they can throw pretty fast. Let's say they're going to throw something with an initial velocity of 25 meters per second. That's like 50 miles an hour-ish. And that would be the magnitude of this vector. And let's say they're going to throw it at an angle of, that looks like about 30 degrees. And I'm not specifying, so that means 30 degrees above horizontal. All right? So what do? Well, the first thing we need to do is we need to recognize that the horizontal and vertical parts of this motion we are going to treat separately. And if we're going to do that, then this launch velocity here at this angle is not what we need. What we need is the components of that. So the first thing I need to do is take that launch velocity and break it up into its components. Components of vectors should always be done in dotted lines. The reason we do that is we don't want to make it seem like there are actually three vectors. Like this is the real deal right here, and these are the two pieces that we're breaking it up into. But solid lines there would not be appropriate because that makes it seem like there's this and then there's these other two vectors. And there's only one, this vector, and these are the components. So we do them in dotted lines. Okay, so here that's going to be 12.5 because the sine of 30 is a half. And then my calculator tells me that my batteries are low and that 25 times the cosine of 30, if I'm in degree mode, is about, if I rounded to, let's see, I rounded that to the nearest tenth, so if I wanted to be consistent with that, that'd be 21.7 meters per second. So what are these things? Well, this is horizontal. This is the constant horizontal velocity. What's this? This is the initial vertical velocity. And gravity, as soon as this thing leaves this person's hand and becomes a projectile, gravity is going to start subtracting 9.8 from this every second that goes by. Right? Okay, so then I'm going to set up two columns of information here. This, in the vertical direction, this is a kinematics problem. So I have acceleration, initial velocity, final velocity, delta x, and time. I think I'd like to encourage you to list time last here. I'll explain why in just 1 second. And in the horizontal direction, it's a constant velocity problem. So in constant velocity, I do not have all these variables. I don't have acceleration, so I don't need to list that. And I don't have two different initial final velocities because the velocity is constant. I just have the constant velocity, the displacement, and the time. So are these two completely separate problems? Yes, except for the fact that the time is the same. The time is the only thing that's the same for both of these. Initial final velocity in the vertical direction, that's totally independent of this. And the delta x, ooh dear, should not be a delta x, that should be a delta y. And I think it's really important, if you've been kind of sloppy or a little loose about what you called this, didn't really think about whether things were going horizontal or vertical, obviously it's very important here. So sorry about that little slip. Glad we caught it. So the only thing anyway in common is the time. So let's go through and fill in what we have. The acceleration, vertical direction, is negative 9.8. I'm going to stick with my convention of always making negative down. The initial vertical velocity is this. The final velocity is, I don't know, and I don't think I really care either. I guess I didn't ask a question. The question here is, where will it land? What's the delta y? I need one more piece of information here. How tall is this building that I have never been inside? Let's see if it's got 3 windows, maybe 15 meters? How about that? So where will it land now that we know how tall the building is? So that's that delta y. So is the delta y 15 meters? You think about that for a second. It's close to being right, but the delta y, this object is going to go from here to here, so the delta y is negative 15. Now, here's one point where a lot of students get confused, hung up a little bit. You might be thinking to yourself, wait a second, the delta y should be more than this because it's going to go up before it comes all the way down. That is true, but that's not what delta y means. Delta y is final position, ground, minus initial position in the vertical direction. And regardless of how much this goes up or not, the delta y, the displacement, is from start to finish, not what happens in between. So the delta y is negative 15. All right. The time, I don't know yet, but this is looking good because I have 3 things here, and as you know from kinematics experience from chapter 2, you need 3 things to be able to find a 4th. So that looks good. In the horizontal direction, my Vx, my constant velocity, is 21.7 meters per second. And that's all I know. I think this is the thing. Where will it land? That's the thing we're looking for here. So this is what we need to do. On the vertical side, we're going to use these 3 things to find time, recognize that the time is the same, and then use that time to find this. Right? And that's what these problems feel like. On one side or the other, depending on the context, depending on what information you have, you're going to figure out what the time is from one side and then import that over to the other side and finish the problem there. So let's go ahead and do that. So in the vertical side, this looks like a delta y equals 1/2 at squared plus vit. Delta y minus 15 is equal to negative 4.9 t squared plus 12.5 t. That's a quadratic formula, or probably better to just do graphing method here. There's a whole bunch of stuff in my calculator. And need to move this to the other side. So negative 4.9 t squared plus 12.5 t plus 15. Number one mistake, maybe number one mistake, but high on the list, is that sign mistake with this, right? having that wrong sign. So if things seem to be going wrong for you, like look for sign errors. That's the number one thing that usually trips us up. Let's see what my window is. 0 to 10, that's probably good for time. I don't think it's going to be in the air for more than 10 seconds. And then it's not going to go into negative y territory. That would be below ground. And it's starting at 15 and going to go up some from there before it goes down. So I could make this, I don't know, maybe 25. See if that's enough. I don't really need to see the peak to be able to find what I need. Alright, so there you go. Now, before you get all excited and you're like, oh cool, that's like a picture of the trajectory of the rock. It's not actually. This is a graph of the vertical motion of the rock. This is the vertical position, y, and this here is time. This is not an x-axis of position, right? This is stretched out. It looks like it's doing that trajectory thing because it's stretched out over time. So we need to figure out where it gets to the ground here, what the time is here. So that looks like it's between 3 and 4, so I'm going to go do my second calculate and find that 0. And I don't want to play the cursor game. I know it's between 3 and 4, so I'm just going to type those in. So 3.44, I'll stick with my 3 sig figs, 3.44 seconds. The time is the same because it's the same projectile, horizontal, vertical. And then here I have delta x is equal to Vx times t. So delta x is 21.7 times 3.44. Which is about 74.6 meters. There you go. That's how you do a projectile motion problem. So a couple other things that I want to emphasize. If you look here at all of the information that we got from here, notice that this 25 does not show up anywhere. That number is the launch speed, and it needs to be broken up into these components. Now, another very common mistake I see is this number showing up somewhere over here. No, it does not. Another common mistake I see is listing acceleration, all 5 of the kinematics variables in both of these columns. But the horizontal motion is constant velocity. It only has these 3. Constant velocity, no acceleration. One of the things to look out for, if you make a little picture, I think it's helpful to do that. I find it very helpful to organize my information in some kind of diagram. If you find yourself listing out all the information and it seems like you don't have enough, think about things that might be equal to 0. So, for example, oh, my nice G2 pen. Dead. Alright, so a couple things to look out for. I'm going to call it a ground to ground. It doesn't have to be from the ground, but a situation where you're launching like this and the same height. So like, kicking a soccer ball, throwing a football, or whatever. In these problems where you're ground to ground, it's not going to say it in the problem. It's not going to list it as a number in the text of the problem, but the delta y is equal to 0. And in my experience, students often miss this, and you're going to need that information. Why is the delta y 0? Because the difference between the starting height and the ending height is 0. Right? and you're thinking to yourself, but there's delta y, like it's going up and down again. That's not what delta y is. Delta y doesn't care about what happens in between. It's just final position minus initial position. The final y position here is 0, and so was the start. All right, so watch out for that. And the other thing I want to alert you to is a horizontal launch. So there, if your launch speed is all horizontal, then that's at 0 degrees. So when you set up your vertical and horizontal, your initial vertical velocity, how much of this is vertical? What's the vertical component of this? Nothing, 0. And what's the horizontal component? The horizontal constant velocity is the magnitude of this. It's the whole thing. So that's another place where students get a little bit confused about what should go here and here. This is all horizontal and no vertical. Right? I think that's all you need. And please feel, I want you to feel like it's a good way of doing things to like try a problem and then look at the solution video right away for that problem, check your answer, and kind of work through it with me. You don't have to do all of the problems to like struggle through all of them and then go to the video. You can make that an interactive process, so long as you do a lot of pausing of the video and don't let me take over. So for example, if you got stuck on a problem and you start watching the video and at some point you're like, I see what's going on. I think I understand what I was doing wrong and what the correct way forward is. At that point you should stop the video and take over and try to get it to the end yourself. And then you can go back and fire the video up again. So I think that's a good way of doing things, kind of like we're doing it together.